Okay, so it is Wednesday, February 3rd, and this is Psych 222. And we continue on with Chapter 3. Last time we talked about graphical approaches and visualization of data. Today we start into talking about central tendency and variability and a few other things of percentiles and interquartile ranges and things like that. So remember last time we talked about the idea that if you have a set of data, that data can range in the thousands or even the millions of observations. So there could be a whole bunch of observations in here. And the idea is to get some kind of a summary of it, some kind of a reduction of the data. Because look, if there's 10,000 observations here, we cannot interpret each value. So we try to reduce our data down. Well, that's exactly what measures of central tendency and variability are about. As the word suggests, central tendency denotes the idea of where the data tend to fall, right? Well, where does the central point of the data seem to be? But that's a very crude designation of what these measures actually assess, because there's different ways of measuring central tendency. So if I have data here that go from 0 to 100, how do I get a measure of that central tendency? Well, we may think of computing the arithmetic mean, and that's the average of observations. And we all know what the mean is. So, when you take a test, you ask the professor, you say, well, what's the average of the test? So we know what the average is, and we'll discuss its formulation pretty soon. But there are other ways of assessing central tendency, which include the median and the mode. So this is not the only way of doing it. And we need to understand that central tendency is not always going to be one-to-one with the average. The other idea here is we need to discuss the idea of variability. How much dispersion is there in the data set? So how do we numerically describe that? So again, if I have numbers 5, 5, and 5, well, how much variability is there? There's no variability because they're all the same value. So we need a way of indexing that variability. If I change this to 4, all of a sudden I do have some variability. If I change this to 400, I have a lot more variability. How do we measure variability? The idea of statistics and parameters, when we're talking about figures for a population, we're talking about parameters. When we're talking about measures for a sample, we're talking about statistics. So we want to calculate statistics so we can learn something about parameters. Okay. So if I calculate the sample mean, I want to use that to get an estimate of the population mean. That's the big idea of inferential statistics. So let's look at some of these measures of central tendency, and we'll see that some of this stuff we're going to gloss over because it's not too important. We want to focus on the most important stuff. First one is the mode. Well, the mode of a set of measurements is defined to be the measurement that occurs most often with the highest frequency. So that's a pretty easy one. When you look at these measurements over here, well, what's the modal selling price? The modal selling price is 27,500. Why? Because it occurs the most often in the data set. Let's go to a smaller data set here. If I have data 2, 2, 3, 3, and 3, 3 is the mode. It occurs most often. What if I have 2, 2, and 3, and 3? Well, technically you can say there is no mode, or if you really want to, you can say there's 2 modes, and that would be okay as well, so long as your audience knows what's being communicated. Don't worry about situations like that. Here, the mode is clearly defined. Okay. The median. Now, the median is important because it's defined to be the middle value when the measurements are arranged from lowest to highest. Now, what does that mean, the middle value? Well, it actually means that central value in your data set. So if I take a data set here, 2, 3, 4, 5, and 6, the median value is the middle value. So it's equal to 4. Notice that the 4 splits the data set into 2 parts. There's the first half, there's the second half. That's the characteristic of the median. Notice that the median does not care, that's a 4. Notice that the median does not care about the values of these. It only cares that they are arranged from lowest to highest. Now, why is that important? That's important because watch. I'm going to put a 60 here. I changed this data point from a 6 to a 60. What's the median? The median is still equal to 4. What if I change this to -2? The median is still equal to 4. That's very, very important to understand about the median. So when we say that the median home price in Missoula is, say, 200,000, I don't know what it is, but let's pretend it's 200,000. And somebody sells their house for, say, 2 million, when maybe they bought it for $1 million. Well, that median home price still stays the same, because even if you change those extreme values, that central value will stay the same. Now, there's some disadvantages to that, because it's not incorporating that 60. It's not incorporating the -2. It's not looking at the sensitivity of the values. So what measure would look at the sensitivity of the values? Well, something else, right? We need another measure to incorporate that sensitivity. So we can say that the median is pretty insensitive to the actual values of the scores. It just cares about that middle value. Okay. As we're going to see, a measure that is much more sensitive is going to be the mean. That's what we want to focus on. So there's some data, the computation of the median. One note about the median here is the way the book is computing the median is that if the median occurs in the middle, well, then you just take the average of those two scores. 84 plus 86 over 2 is 85. So why 85? Because 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It's the 85 number that's splitting that data into two equal parts. And that's kind of meaningful, because we notice here that the median does not even have to be a number in your data set for it to be called the median, right? Which is kind of interesting, because if I told you that the median is 85, you might at first glance think that 85 has to occur in the data set, but that's not true. The median could not exist, yet it still be called the median. Okay, so other examples of the median here. Make sure that when you're computing medians, here's the biggest error that people make computing medians when they're doing it by paper pencil, is that they fail to put the data in order. Okay, that's very, very important that you put the data in order. If you don't put it in order, you cannot simply look at the values and then get the middle value, because that will not be the median, right? So if we try to take this value, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, this is not the median, because the data set is not in order. This is the correct place to look at the median, because the data set is now ordered. And we see it's 4.5 over here. Very, very important. Okay, make sure you order it. So imagine you get a question on the test that asks you to compute the median, but it puts the numbers in a different order, like 3, 2, 6, 8. Make sure you don't just go in here like that. You have to order it first. Okay, the median for group data follows the same principle. You don't have to know this or know how to compute it, but you should know that if you have group data, that the median can be computed. So remember, we talked about frequency tables and class intervals and things like that. Well, we have frequencies per interval here, and we have the cumulative frequency. Well, you can compute the median of that as well. And that's what software will do, is use frequency distributions like that and compute the median. This computation, however, is not important for us to learn. Just understand what the median is based on our examples, and you're good to go in terms of understanding the median for what we're doing. Now, the arithmetic mean is very, very, very important. That's another measure of central tendency. And we say that the mean of a set of measurements is defined to be the sum of the measurements divided by the total number of measurements. So we all probably know what a mean is, but it's worth just talking about it briefly, there's your mean. Okay, there's your mean. So what are we doing when we calculate the mean, the arithmetic mean? Well, one note here is, why is it called the arithmetic mean? It's called the arithmetic mean because there are different types of means out there. There's a harmonic mean, there's the geometric mean. So when we just say the mean, we're usually referring to the arithmetic mean. However, if you hear a researcher talk about the mean, maybe worth just double checking to make sure that it's the arithmetic mean they're talking about. In this book, right now, we're simply talking about the arithmetic mean, and it's defined this way. So taking the sum of observations divided by the number of observations that went into that sum. And in this sense, the mean is a balance point. It's kind of like the center of gravity. It's very, very sensitive, right? It's very sensitive. Remember, we said the median is not sensitive to the values of the scores. The median is simply wanting to know that middle point. Well, let's go back to a little data set here, 2, 3, 4, 5. If I change the value of this 5 to 500, what happens to the mean? Well, the mean gets pulled up in the data set, right? Because it's taking the sum of values, dividing by the number of pieces that went into the sum. So we can see that the mean likes to incorporate that particular value. It's not simply just happy with the number 5 as a placement. It wants to know how big this value is. Home prices. So what did we say? 200K? Let's say that's the mean. Okay, let's say that's the mean, X bar. Some rich celebrity from California, Hollywood, comes over to Montana, and they decide they're going to buy a really, really, big house, and they don't care what it costs because they have so much money, it doesn't matter. So let's say the selling price for the home is $5 million, and they come over and they say, why? Let's pay 6 or 7 million. What the heck? And they pay a lot of money for the house. What happens to the overall average house price in Missoula? Well, it increases because it's being pulled up by that $6 million home. It's not simply, the mean is not simply happy with recording a value here. It wants to know the particular number, not just that there's another home price. Okay, and that's what differentiates the mean from the median. It's very sensitive. We look at the computation here. There it is. So the sum of, I'm using X up here. The book is using Y. Remember, whether you're using X, Y, Z, these are simply variable names. So it doesn't matter, but I'll go back to using Y here. So there it is, Y bar over N, sum of all the Y values. We can talk about the population mean. We can talk about the sample mean. Sample mean, little y bar, and the Greek letter read mu, that's the population mean. So there's the mean. And we hear averages reported all the time. And it's important to understand that sensitivity to the values, because otherwise they can be a little bit misleading, okay? If you don't understand that it's sensitive. So again, if I have that small data set, now if I have a big, big number here, well, the average of this is going to be pulled up towards this, and it's going to be entirely misleading because there's 3 numbers here that are really low, and then I have a huge number. So we need to be aware that there's a computation of the mean using their example. Now, using it for a frequency distribution, again, we don't have to go through the details of this, but you should know that you can compute averages for frequency distributions. And what that's going to do is incorporate the frequencies of the given intervals. So we have our frequencies over here in our intervals, and we can compute an average of that. But again, that's not vital information. So we don't have to know that. You're not going to be asked on that. But you should know that if you're reported a mean, it could be coming from a frequency distribution. But these types of computations here, as you'll see as we go through the book, this does not really afford very much insight into what the average is. And as we go through the book, we're focusing mostly on those things that are very, very important for understanding how statistics work. This is not that important for understanding statistics. We may have outliers in distributions, and we will define outliers more as we go on throughout the course, but these are extreme values, and they pull the mean in the direction of the outliers to find the balancing point. This is exactly the concept we just talked about with that huge number of whatever, 5 million or whatever it was, that's going to pull the average up. Again, the lower home prices will pull the average as well, right? 200K, a home sells for 10K. Well, that's pulling the average down. Sometimes computers like to report trimmed means, and trimmed means, what they'll do is they'll drop the highest and lowest extreme values and average the rest. So sometimes it drops the highest 5% and the lowest 5% of the distribution. And that's to try to get a handle on outlying scores. So you may have 3, 4, 5, 6, and then 700. Well, it's going to try to get rid of some of those extreme scores on either side. Maybe that's negative 30 or something. Takes away those 5% on each side. Sometimes you'll want to interpret the trim mean. Sometimes you don't. Sometimes you just want to look at the data set to get an idea of what those scores are. But you should be aware that the trim mean will do that. It will not be the same across all software programs either. Sometimes it's 5%, maybe other software programs is 2.5%. You always need to read into what the software is actually computing. You don't want to fall into the trap of thinking it's always the same because you could be misled. Now, the skewness of the distribution, we talked about the skewness of the distribution last time. Well, when we look at a bell-shaped distribution like this, we see that the measures of central tendency fall toward the center of the distribution. Trimmed mean, the average, the median, the mode, they all fall right at the center part, if that is a perfectly mound-shaped distribution. Now, this is in theory only, because with real data, you're never going to get a perfect curve like this. That's never going to happen. But in this kind of idealized context, everything's going to fall in one place. But when you look at skewed data, well, what's going to happen here? With skewed data, notice that the average is being pulled, right? The average is being pulled towards the more extreme scores on this end of the distribution. And that's exactly the concept we developed just previously. We said that if you have extreme scores, that average is going to be pulled by those scores. The median, less so, right? The median is over here, so it's not being pulled by the values of those scores. It's being pulled by the number of values over here, but it's not caring whether this is a negative 30 or whether it's a negative 300. It just cares about the number of scores on this side. And then the mode is what the mode is, okay? So you should be aware here that averages are pulled. They're very sensitive to those scores in the distribution, where the median is not sensitive. It just cares about the number of values. If we go the opposite way, distribution skewed to the right, we can see the opposite effect. See how that average is being pulled this way? And that mirrors what we talked about with our home price example. This is a very useful summary here. Major characteristics of each measure of central tendency. So you can look at this as just a summary of what we've talked about. Again, don't worry about the group data. That's not very important, but this summary in the book is really, really nice in terms of what they talk about, and really good summary there. Okay, describing data on a single variable, measures of variability. Well, we talked about the idea that we want to get the measure of central tendency, which will often be the mean, but now we want to get a measure of how different scores are from one another. Okay, so let's use a grading example. Let's imagine that I told you that the average on test 1 was 70%. Well, that tells you the arithmetic mean, but it does not tell you how much variability there is in the distribution. So if I simply give you the average, you don't know where people scored on the test. For instance, it's entirely possible that everybody got 70%. right? If everybody got 70%, the average would be 70%. But it's entirely possible as well that we have scores ranging from 20 to, let's say, 99, and the average is still 70%. So what we want to talk about is how to assess the variability in a distribution. What could we use to measure how much scores differ in the distribution? Because that is really, really important as well. If you go back to home sale prices, again, if I told you the average home sale price is 200,000, well, how much does that vary, right? How much variability in the distribution? Some home prices may be 10 million. Some home prices may be 10,000. You want to get an idea of how much difference you have. That's what we need to develop, the concept of variability and how to measure it quantitatively. Well, one measure to measure variability is the range. What is the range? Well, the range of a set of measurements is defined to be the difference between the largest and the smallest measurements of the set. So we can immediately see that the range is not very useful, right? It's not very useful because if I take any data set and I have the lowest value and the highest value, it does not tell me what's going on in between. It simply tells me the lowest and the highest. So imagine if the the maximum sale price of homes in Montana was, say, 10 million, right? 10 million. And the lowest home sale price was a home given out for free, right? Zero. Somebody didn't want their home, so they actually just gave it away. And they said, you give me nothing for the house and I will give you the house. Well, what's the range? The range is 10 million. How uninformative. It does not tell you what's going on in between, and doesn't even tell you anything close to the average, the median, or what that distribution looks like over here. So we need a better index of variability than the range. The range is just not good enough. For group data, we don't have to bother with that for group data, but you can compute ranges on group data just as you can for ungrouped data. But again, the concept here is the range is not going to tell us that much information. Well, let's just make a quick pit stop here and talk about the percentile. So the percentile of a set of n measurements arranged in order of magnitude, again, put it in the order of magnitude, is that value that has at most p% of the measurements below it and at most the balance of that above it. So we know what a percentile is, even before studying any of this. There's a distribution. We can see the distribution contains 60% of scores below and 40% above. That score, whatever score is in the distribution, is the 60th percentile. Why? Because 60% fall on this side and then the balance fall above it, right? The balance of that 100 minus p% is above it. If we look at this distribution right here, that nice bell-shaped distribution, we can look at different percentiles in there. We see that the median is going to fall at that 50th percent, right? Because half of the scores are on this side and half of the scores are on this side. We have 50%, we have 50%. These here are called quartiles of the distribution. We have the first quartile, that's the first, or the lower quartile, and that's at the 25th percentile. And then we have the upper quartile, which is at the 75th over here. And the median is that 50th. So that's what we need to understand about percentiles. And again, I want to emphasize that all of this looks familiar and we know what percentiles are even before looking at that. We have an idea of what they are. So if I told you, if you take the GRE, the graduate record exam, if you're thinking about going to graduate school, well, you'll need to take a general test. You might need to take a specific test of the domain that you're interested in studying. For instance, if you're going into psychology, you might have to take a psychology specific test. Well, when you get your scores, they will report things like percentiles. So if they reported a percentile of, say, 70%, well, then you're scoring better than 70% of people who took the test on that day. right? If you have a 99th percentile, wow, you're scoring better than 99% of people on that day. If you have the 20%, well, then you're not doing very well because you're only scoring higher than 20% of people who took the test on that day. So that's what percentiles are about. Don't worry about computing the actual percentile. Again, there's some formulas here given for computing it, and there's also some formulas for computing the percentile based on frequency distributions, but you don't have to worry about that. Just understand what we've talked about, and you're fine for that. Again, you can go through these computations, but you're not going to be tested on them, and these computations will not offer a lot of insight into what a percentile is. And if we did go in these computations, we'd be spending a lot of time computing percentiles, but we have more important things to get onto. Now, another measure of variability is the interquartile range. Now, that's pretty interesting because the interquartile range, having defined the quartiles, the interquartile range is the 75th percentile minus the 25th percentile. So when we look at that distribution here again, and we say this is Q1, Q2, and then Q3, now the first quartile is at the 25th percent, and this is at the 75th percent. What the interquartile range will do, will take the 75th percentile, whatever that score is in the data, minus the 25th percentile. So notice that the interquartile range is trying to focus on this area of the distribution. Now, why would we want to compute that? Well, we might want to compute it because we want to kind of not talk about those more extreme scores. We want to get an idea of where that range is on the inner part of the distribution. And that's one reason for computing the interquartile range. Okay. So we have the range, we have the interquartile range, which will leave out this stuff, and those can be used to measure variability. But again, we want to stress that simply because you compute the interquartile range, it does not tell you what's going on in here, right? It doesn't tell you what's going on in here. So again, if I told you the interquartile range of home prices is 100,000, how much information does that really tell you? Not that much, because they're simply taking values and subtracting other values, but not telling you what's going on in here, not telling you the specifics. Okay. Talking about deviations here, well, we have to talk about deviations to get to this thing called the variance. When we say we're taking a deviation in data, we're taking a given value minus another value. Now, often that value will be the average. So if I take a certain score in a distribution, I may want to subtract the mean of that distribution. Now, why would we want to do that? Well, let's get on to computing what's called the variance. Okay, so again, some of the parts in the book, I'm going to tell you that's not really important. You can read over it if you want to, but it's not extremely important. This is not one of them, right? This is extremely important. So you're highlighting this, you're marking it. You're going to see questions on the assignment. Understanding what the variance is really important. So let's define it. The variance of a set of n measurements, so you have different measurements, right? Different data points, with mean, so it has a mean, is the sum of the square deviations divided by n minus 1. So the sum of the square deviations, we just defined a deviation just above as y sub I minus the mean. What the variance does is it takes the sum of all those deviations and it squares them. Now, why are we squaring deviations? Well, we said that the mean is a balance point and a center of gravity in a distribution. So if I have different scores here and different scores here, what the mean tries to do is it tries to balance things out. Notice that this is perfectly balanced. It's not going like this or like this. It's perfectly balanced. So if I take the sum of deviations from the mean, so y sub I minus the mean. So imagine that the mean here is equal to 10, and this score is equal to 15. The y sub I score is the 15. The mean value is the 10. So if I computed that deviation, what would I have? I'd have a deviation of 5, right? There's one deviation. Now let's take another deviation. Imagine I have a 5 over here. Well, 5 minus 10, score minus the mean, is equal to negative 5, right? So I have a plus 5 here, and then I'd have a negative 5 here. Well, that's only 2 deviations, but you can already see that if I sum those deviations, so if I sum those deviations without squaring them, if I just sum those 2 deviations, what am I going to get? I'm going to get 0. Now, in this case, I only took 2 deviations to demonstrate this principle. But I can tell you that if you take the sum of deviations from a data set away from the mean like this, if you take that total sum, you will always get 0. Now, why will you always get 0? You'll always get 0 because that's exactly how the mean is defined, as the balance point. So here's the concept. If you take those deviations from the mean is constructed in such a way that it's trying to produce that perfect balance. So by summing all of those deviations, you're going to get 0 every time. You can try that on any data set you like. This will always hold true. So what do? Well, one solution to that is to square the deviations. If you square the deviations, what happens? Well, let's look at this example here with the plus 5 and the negative 5. The plus 5 squared is 25. The negative 5 squared is 25. Notice that by squaring the deviations, we took care of that negative, right? We managed to get rid of the negative and produce a positive number. So you can see that by squaring deviations, we're setting things up so that we do not always get 0. Putting a line through the equal sign here. It'll let me, there we go. Right? This is the idea of squaring deviations, to get rid of the idea that you're always going to have 0. Otherwise, you'll always sum to 0. So it takes those negatives, produces positive numbers out of them. Now, why are we dividing by n minus 1? Well, we're dividing by n minus 1 to get an average of those squared deviations, right? And remember when we computed, let me just work down here a little bit. Remember we computed the average. We said it's equal to this over n. The sum of y sub I divided by n, the function of n was to get that average. Well, look at what we're doing here. We're dividing by n minus 1. Now, it's not quite the same. Because we're subtracting the n minus 1, it's a little bit different, but the concept is the same. The concept of division by n minus 1 here is the same concept as dividing by n over here when calculating the mean. We're taking the sum of observations, and then we're asking how many pieces of information went into that sum. We're taking the sum of observations, in this case it's squared deviations, and we're asking how many pieces of information went into that sum. For reasons that we will have to delay later in the course, we're subtracting 1 here. But again, get the concept that we're dividing it by a function of n. Okay, and remember what the summation sign means is start with the first value, I equals 1, and sum everything in your data set. So you can say that implied up here is an n up here because we're going to the nth value. So just this means sum up all of those squared deviations. You'll have to do an example of computing the variance in the assignment. And when you're computing it, pay very close attention as to what you're computing and when you're squaring things. Very important number. Now, this number is going to give you an idea of how much variability you have in your data set. And that number will be a positive number, right? It'll be a positive number if there's variability. It will not be negative because the function of squaring got rid of the negatives. If you have no variability in your data set, then the variance will equal 0. So here's a data set, 5, 5, 5. What's the variance going to be? 0. And you can practice that computation if you like to show to yourself that the variance will equal 0. If I change this to a 6, I'm going to get a variance different from 0. So it's giving us a little bit of a measure as to what's going on in the data set dispersion-wise. Okay, the book does provide a discussion of division by n-1 makes it an unbiased estimator. I will return to that later in the course. They do not talk about it very much here. They don't talk about it enough to really understand what's going on here. So that's why I want to delay that a little bit. But if you do read that and you follow that, that's great. But we'll return to that point as to why n-1 is being used. The standard deviation is another useful measure of variability. Now, what's the standard deviation? The standard deviation is the positive square root of the variance. So when we computed the variance just now, right here, remember we squared deviations, right? We squared those deviations. Now, why did we square? Again, to get rid of all those negative numbers. Well, when we report it, this is going to be in squared units. So imagine if I took an IQ test and I gave that IQ test to the whole class and I calculated an average, and the average was say 100. So the average IQ test is the average IQ is 100, and the variance was equal to, let's say, 25. Okay, this was the variance, VAR. Well, this is in squared units, right? This is in squared units. So if I told you how much variability there is in the class on IQ, and I told you it's in 25 squared units, that would be very awkward, right? If I told you on average scores deviate from the mean by 25 squared units, you'd say, why are you reporting it in squared units? That is very awkward. And it is awkward, but we had to square to get rid of those negative numbers. So why don't we report it in the natural units of the variable and take the square root? When you take the square root of all of this, it will return the units into their original units instead of squared units. That's exactly what the standard deviation does, is it returns the units back to their regular units. So you do not have to talk about squared units, because squared IQ units is just very awkward to talk about. So you take the square root of it. So if I take the square root here, I'm going to get the square root of 25 is equal to 5. That is the standard deviation. Okay, the standard deviation. Again, you'll notice that I've spent a lot of time here talking about the variance and standard deviation because those are very, very important concepts. Standard deviation, variance, really, really important because they are indexes of variability that are going to serve us throughout the rest of the course. And it's really important that we understand how they're computed and what they're really telling us. So these formulas here are really, really key. One note, when we use S, we're denoting the sample standard deviation. And when we use this symbol sigma, looks like this, if I zoom in a little bit, that denotes the corresponding population standard deviation. Usually we're dealing with sample data, so we're computing this. But recognize that if we had our choice, what we'd really want to know is this, right? We want to know the population standard deviation. We have to settle on the sample because we usually don't have the population standard deviation. An example of computing the standard deviation and variance. So notice that we have our y-scores. We are subtracting the mean. So this is y sub I minus the mean of the data. If you sum those up, what do you get? You get 0. So that's why we are squaring the deviations, and you get 8.80 divided by n-1, and there's the variance of that data set. Okay, again, book talks about frequency distributions. Don't have to know that. The formula is a little bit different because it uses the frequency per interval. But again, don't worry about the frequency distributions when computing these things. You really want to focus on those concepts, though, of what's being computed for the variance and the standard deviation. The frequency distribution computation does not provide additional insight into that. The mean absolute deviation, the median absolute deviation rather, we will simply define this now that sometimes we do not take deviations from the mean. So, above when we computed the standard deviation and the variance, we were using deviations from the mean. Sometimes it makes more sense to take deviations from the median value. And this is the median of the absolute deviations of the n measurements, about the median. So you can look at that a little bit. It's not of high importance, but you should understand that sometimes we like to take deviations from median values as well. And there's an example of taking deviations from the median that you can look through. Again, I wouldn't focus too much on all of these computations in terms of a procedure. Just get the idea of what they're computing there, and that'll be fine. Okay, let's finish off for today by simply talking about this empirical rule that when we look at distributions, we'd like to know overall, what does the distribution look like in terms of averages and standard deviations? Well, the interval here, let's see if we have a picture of this coming up. Well, let me draw one over here just to get us started. This is known as the empirical rule. So if I take a distribution like this, now that's supposed to be a normal distribution. Okay, I've tried my best. And I put the average over here. Well, this is 1 standard deviation, 2 standard deviations, and 3 standard deviations. And this is, on the other side, my standard deviation bar. So I have 1 standard deviation, 2 standard deviations, 3, and then I'm going to put negatives over here to indicate standard deviations on the other side. Well, this empirical rule says that given you have n measurements possessing a mound-shaped histogram, I've drawn this as a distribution, the interval of the mean plus a standard deviation. So what's a mean plus the standard deviation? Here's the mean, plus a standard deviation on this way, plus and minus a standard deviation on this way. So this symbol here is plus minus. So we're going either on this side or this side. What you're going to find in here contains approximately 68% of the measurements. If you go out towards 2 standard deviations, then you get, in this range here, about 95%. Now, those are approximate figures. It's not exactly 95%, but it's approximate. And then if you go to 3 standard deviations, you are going to get about 99.7%. Now, why is that important? Well, that's important because imagine if I told you the average of the test was equal to 70, but I told you that it followed a normal distribution like this. Well, then you can figure out, if I told you the measure of standard deviation, approximately how rare your score is. So, of course, you scored up here because you're doing really well in the course, and you're up here. You can determine by this approximately how many people scored like you, right? And what would be that expectation of scores in that end of the distribution? If I told you you scored within the first standard deviation, well, then you're in that 68%. If I told you you're within 2, then you're in that 95%, and within 3, you're in that 99%. So we can use these empirical, the cutting up that distribution to give us an idea of those percentages under the curve. And we will see more how to do this as we go on. Okay. Another example of the empirical rule given over here. Okay, let's stop there, and we will start here next time and just recap this. So we're going to apply these to the actual histograms, what we just talked about in terms of the empirical rule. And then we're going to talk about box plots and a few other things as we complete the chapter. So we're going to finish this off on Friday, and then next week we will already be into chapter 4. Okay, so we will see you on Friday.